Hey, welcome. Wait till you see what part 3 has for you. Some very interesting stuff here. If you look around the screen, some things will be familiar and some things are going to be different. Let's come over here. While we're looking at Scalar Product, we've done that in 2D, so you might have to go back to earlier presentations and have a look at the Scalar Product in 2D. We are going to pick it up part way through there, so just remember what we did. We sought out a way of finding the angle between two vectors and came up with this interesting product, which we call the scalar product, because it's just a number. It's not itself a vector. And it was an interesting combination of the components of the two vectors. So a scalar product is not just a product, it's the sum of the products of the components. And this was what we found. So we're going to revisit that later on. And the idea of finding an angle between two vectors was the way in which I thought it should be driven, so that you come across this scalar product in a fairly natural way. Look over here on this side of the screen. Hey, we've got some interesting things happening here. Two vectors, and if you like, you can consider them to be defining a plane in space, couldn't you? If you have two vectors, you can draw a flat surface between them and generate a plane. And what about this? N for normal. This vector is perpendicular to that plane. So the idea of a vector product is to find a vector perpendicular to two others, or perpendicular to a plane. And I don't know whether you've done any physics, but does this look familiar? A charge moving in a magnetic field, and the forces are is at right angles. Here's a right-hand rule. I guess you've done that if you've done some physics. So we're going to see that application a little in our vector product now, where we're generating a vector perpendicular to two others. So that's an exciting application. And at the end, I've got a little question for you about where you think the work in this section of vectors might lead you in 3D land. So wait for that right at the end. Anyway, let's get started and see what you think. Here we go, the scalar product revisited. Okay, so here's the definition in 2D, the dot product or scalar product, dot product because we use that symbol, and guess what, we're going to use this symbol for the vector product. So we've got the two sorts of products, so this is sometimes called the cross product using a cross multiplication, and this one the dot product. So it's A1B1 plus A2B2. The x coordinate of the first vector by the x of the second plus y of the first by y of the second. Okay, and we came at it from this point of view. We found that to find the cos of the angle between vectors, then it was that strange product divided by the two lengths, or if you like, the dot product is the length of one by the length of the other by the cos of the angle between them. Okay, now because it was all based on lengths, now 3D vectors are going to be exactly the same. We need to explain that. It was all based on lengths, if you remember, and the length expression for the 3D vectors just involved another component. So actually now, if we have that other component, the scalar or dot product is the product of the two x's plus the product of the two y's plus the product of the two z's. That's the idea. So it's a fairly natural extension coming from lengths, and I'll just do it here for you a little bit, coming from lengths. Being the same basic formula, another Pythagoras giving you another square root of z2 take z1 squared on the end. Let's have a look at what we did. Here we said that vector is A take B. Sum of vectors around a closed figure, if you like, going from there to there. And what we did was to use the cosine rule for this angle here. Okay, if you remember, the cosine of theta was what we're after. So we said the length of A take B all squared equals the length of A squared plus the length of B squared take 2 times length of A, length of B cos theta. And of course we can find all of these A take B if we call A A1, A2, A3 and B, B1, B2, B3. I'm not going to go through all this again. We did that in a 2D presentation, just give you an idea though. So A take B is A1 take B1, A2 take B2, AC. It's just another component on the end there. And when you find the length of it, here it's going to give you just the same stuff again, but with that A2 take B2, with that extra component. So you might like to finish this, and here of course, same thing. So squaring both sides later on, A1 squared plus A2 squared plus A3 squared, and you could try to complete it and see if you do come up with what you should have is rearrange it. Cos theta would equal to the dot product, oops, left out a square there, a dot product A dot B in 3D land over length of A by length of B. That's how it should come out. So try that anyway, and that will just validate the idea we've just got another product of components on the end for 3D dot products or scalar products. Okay, so the rules are the same for the same reason. You can go through and prove them with an extra component. A dot B is B dot A, it's commutative. A dotted with itself is the length of A squared, because cos of naught is 1. If you remember that, A dot A equals length of A by length of A by cos of theta, cos of naught, the angle between A and itself, cos of naught is 1, so it's length of A squared. And these ideas here that you can, if you like, operate over, or the distributive rule over addition here if you like, and then our expansion of this with the dot product is similar to FOIL, of course, in algebra land. Okay, so you could use the general vectors, and there's some of those coming up, to prove that that's the same. Okay, so you do the left-hand side and then do the right-hand side, all in vector components here, and show they come to be the same thing. All right, so let's have a reminder of the geometric properties of the scalar product. And I've just done it back there actually, because I like to think of the scalar product as coming about by trying to find the cos of the angle. But here's a different proof, if you like. So what these screen clippings are from Hayes and Harris, so you might have a look at their book there. One vector is translated so that both vectors emanate from the same point. And let's call that point the origin, if you like. So that's log without loss of generality. So we can actually move them around, and then you wouldn't lose the general nature of the result. So here it is, OA is A, OB is B. Oh, they've done the other one now, going the opposite way. B take A because of some of vectors around a closed figure. Now by the cosine rule, there it is. But this time we're going to just leave it in length form here, and then we can use our rules here, the dot product rules, to do that, and that generates then that result. So that's doing it slightly differently if you know what that dot product is. I like the other way of above that we just did, of trying to find the angle between them and thereby generating the idea of A1 B1 plus A2 B2 plus A3 B3. Anyway, so an interesting little proof here, linking it to this geometry. In this course, the geometry is very, very important to know what's going on around a figure like this. Okay, let's go on now and have a look at doing something for non-zero vectors. So if the vectors aren't themselves zero, then, and you got a dot product, a scalar product is zero, then it means they must be perpendicular. And I just mentioned that before, because the dot product is zero, these two are not zero, cos theta must be zero, that means theta must be 90. Okay, so theta is 90, means A and B are perpendicular. So there's your definitive thing. If A dot B is zero, then the vectors are perpendicular, and you can use that routinely now. Okay, let's have a look at this. If A and B are two vectors, we did a bit of this in 2 dimensions. We're looking for the projection of A onto B. That is like a wind on a boat. How much does it assist the passage of the boat, so in the direction in which it's steering? All right, so here's our component, and you can see that this length here divided by A is the cos of theta. So therefore multiplying across, that is A cos theta, and if you look at A dot B, that's the length of A by the length of B by the cos of theta, and you want A cos theta, so that's A dot B divided by B. So the length of this vector, A cos theta, is this expression, so there it is up there. Oops, length of B. And then that's the length of the projection vector. If you want to make a vector in the direction of B, then you would use the unit vector, what we've done before. Pinch B's direction and divide by the length of it. So if you like, you want to capture, this is a Huddyism now, you want to capture B's direction, if you like, only. You don't want any length, you want it to be unit length. Okay, so there's another little application of unit vectors. All right, let's keep going. We've got a fair bit to do in this one. Here's a little proof about that, and that's what I've just done here. In that triangle up there, we've said it's A cos theta, which is therefore dividing by B, and therefore you've got the result you want in terms of the length. However, cos theta may be positive if theta is cubed or negative if theta is obtuse. And as the length must be positive, we're going to use that, the size here of A dot B. Okay, so here we don't want a positive, we don't want a negative. That must be positive because we want a positive length here. So you should put this around it. All right, so then multiplying by that, as we said before. All right, let's go on and have a look at some examples and get you going. Here we go, we've got two vectors, we want A dot B. Here it is, product of the two x's, product of the two y's, product of the two z's, got an answer. And we want the angle between them. So A dot B is the length of A, length of B, cos theta. We've got the dot product, put in the two lengths, square root of the x component squared, y component squared, z component squared for both of them. Okay, so we bring those down, multiply them together, divide by it to get cos theta, and it's negative. Look it up on the calculator, and it's obtuse angle. Of course, second quadrant, causes of angles are negative. Let's just revise that. Why? You don't need it actually here because the calculator does it for you. As we come over here, the cos is the x coordinate, and that's negative in that quadrant. So that checks with the calculator, giving you from a negative cosine an angle in the second quadrant, obtuse angle. Projection vector, they ask just for the projection, that's just that length. They ask for the projection vector, you must multiply up the unit vector, so you pinch A's direction, if you like, capturing the direction of A. So B dot A, we've got those, B dot A, yeah, length of that, and we want just 4 now. We don't want neg 4 because this must be positive in here, and then with the direction of A. So we get 2/7 A, and you can put A in then. A was the vector 2, 3, neg 1, and we want 2/7 of it. So just remember there, you're multiplying 2, 3, neg 1 by that. All right, easy enough, some interesting manipulations. You can see this could be useful in practical problems, like a plane flying and you're looking at components of the wind or whatever against the plane and how that's going to affect it. All right, let's have a look at doing some work here. So here's your first little lot, 4F, question 1 through to 7, and then we'll bring up 8 in a minute. So pause the presentation, have a go, and I'm going to show you the answers as usual. Down below you might have to toggle forward as you do them and check the answers. Here we go, let's do some more. 8, 9 and 10. And here's an important point that we saw back in 2D. If you're finding that angle between vectors, you must go out from that point. that vector and that vector. If you have one that is coming the other way, then you'll find the obtuse angle there. So if you want the absolute angle between them, whether it's obtuse or whatever, you must start the vectors from a point and move out from that point. Otherwise you don't get this angle, you get the obtuse angle. Alright, so just check that. 9 and 10. Let's go to 11. And then that's just a whole lot of angles. Alright, I think I've just answered that question, but by the time you go back and do it, hopefully you will have forgotten what I said there. Alright, let's go on and have a look at the answers. 1 through 11. Oh, a bit wonky on the page there, slipping off the edge of the page. Check those, question 1 and 2. Question 3, a lot of work here just proving some of these results here. You should be able to do that. It's just tedious algebra really. Sorry about the page slipping over there. Question 6 and 7. Look at question 8. And 9 and 10. And have a look at 11. There we have it. Alright, how did you go? Might have to think about some of those. Let's move on and have a look. We've got quite a lot to do here. It's an interesting section, so we've got a bit of a gap here. I'll give you a bit of a break. Here we are. Okay, let's have a look at something in 3D geometry now, and this could be very useful. Find the angle of ABC here using vectors. Okay, so you need to set up some sort of grid and make it from this point here, and then we've got the lengths, so that means we can assign coordinates to A and B and C. Just watch C. C is a tricky level, it's the midpoint, so you're only coming out 1 here, not the 2. You're coming out 1 and along 4 and up nothing. So we've got to establish carefully these coordinates on that grid system. Then we want this angle, so it's got to be BA and BC coming out, remember, coming out from that point. BA and BC like that. So what we're doing here is this, BC and BA to get that angle. Okay, must come outwards from the point to get that angle within the two, between the two vectors. So then we can say the cosine is the size of the dot product, that should be around there. Divide, oops, no, that, we don't need that here, sorry, that's all right, we need it, just BA dot BC. We want to know whether it's acute or not. You made a mistake there. BA dot BC, divide by length of BA and length of BC. So there's a fair bit to do with the dot product there and multiplying them out. Okay, so some of them are zeros, so that makes it easier. What have we got? Doing that, yep, that's okay. And the inverse cos gives you an acute angle, as you would expect in that scenario. So that's an interesting way of doing it with vectors. Come down and let's have a look. Here, give you a rest at a couple more problems. So 12 and 13, okay, using it for a little bit of geometry. Geometry is important in this course. So a tetrahedron, working with that. Okay, and come down and we'll have a look at some more, 15 through 21. And then we'll have a look at the answers to those. I think these are pretty much all right. The little rules in here, but they give you a hint. This is an important result. The length of a vector squared is equal to its dot product, because we said A dot A is length of A by length of A cos theta, and theta is naught, so that's 1. So A dot A is the length of A squared. So you can use that. All right, have a go, and I'm going to show you the answers. A few bigger problems here. Notice the assignment of coordinates and bringing in a grid system. Okay, let's go to 13. See what you think. 14. Let's see the rest of 15. And 16 there. 17 and 18. Bit of work there, a bit of algebra. And then 19. The rest of 19. Important idea here, using your geometry. And then 20 and 21. All right, and guess what's just raised its head down the bottom of the page there? Vector product. So I've mentioned this on the first page, and of course what it is summarised best by this diagram, I think, that if you have two vectors, and you can consider them as defining a plane in space, a flat surface, and you want to get a vector perpendicular to them, and we do this in trying to find the equation of the plane later on. So that's a mathematical approach to it all. We want a normal to two vectors or to a plane, and that's going to be useful for us, and it's useful for some other applications which I'm going to ask you about right at the end. But then you have the application in physics where you have forces which might be at right angles. So you're going to find a force which is at right angles to two others here, and this is what? A charged particle moving in a magnetic field. Okay, magnetic field has an effect there, and also the field generated by the charged particle. If you want to do a bit of physics, don't know whether you've done that. But anyway, just a mention here of that, because there is a good application outside of just the mathematical treatment. So that's exciting. Okay, let's go and have a look at it. And so for those reasons, what we're going to try and do is to find a vector x, y, z which is perpendicular to two others. Okay, so what's the first thing? Perpendicular to you should be in the dot product. So A1 by B1, etc. Has got to be, sorry, we want these two perpendicular, starting off the wrong way. So x by A1 plus y by A2 plus z by A3 must be naught, because this is going to be our constructed perpendicular vector to these two. Okay, and then we can do it for the b vector. Now our problem here is we want to solve this for x, y and z. Okay, so first of all we need to probably try to get it in a reasonable form. So we've got neg A3z and neg 3bz on the other side, and solving them we could multiply by neg b1 and a1. So that makes these leading terms here the opposite to each other. So this is solving simultaneous equations by elimination. This is where maths learning being sequential and cumulative, you need to remember this sort of technique, because then we've got the relationship between y and z. You might have realised we only had two equations but three unknowns. So we're not going to be able to solve uniquely for the three. We're going to be able to just get a relationship between them and use parametric equations to indicate that relationship. So when we do it, we've got A1B1, A1B2, take A2B1 by Y equals A3B1. Oh, what a mess. So Y to Z, that ratio, is the ratio of those components. Bit messy. I'm going to show you an easy way of doing it in a minute. So it's a ratio, so as in the last presentation, we really should say this is something by t, and if it is, then this is in that ratio that many lots of t for all non-zero t. Okay, so that's the idea of having a ratio arrangement or relationship between two variables. All right, so then we can go back to the first equation, A1z, and its relationship to y, A1x, its relationship to y and z. Okay, going back up here so that we can now find x. And if we do that and just expand it, then we've got this result, and now we've also got x in terms of t. So because a vector is x, y, z, we can say it's t outside of those components. So this is the simplest vector, which would be perpendicular to the given 2. So let's do that down here. Okay, so the simplest vector is this one here, which has just got those components. The whole family of vectors would be that times t, if you like. And we call this the cross product or vector product, and we've constructed, now this is itself a vector, see? It's a vector, it's got components, so this is the vector product, and it's a vector which is perpendicular to the given vectors here, A and B. And that's going to be a powerful tool later on. All right, so what a mess though. How are you going to remember how to get those? So matrices to the rescue. I don't know whether you know much about matrices, but the patterns that we're seeing here can be linked to the determinant of a 2 by 2. Now, a determinant determines whether a matrix is singular or not. That is, whether it's got no inverse or has an inverse. Okay, so that's where the word determinant comes from. It determines whether it has an inverse. So here, just working with this, if you had that, the determinant is 2 by 5, take 3 by 4. Okay, now this odd pattern here could therefore be summarized by that, and this other odd pattern could be summarized by that. Okay, so therefore the cross product could be summarized by those determinants. But you've still got to remember the pattern within those little 2 by 2 matrices, don't you? Now it might be easier to say this, A2, A3, B2, B3 by I, plus this one, that determinant by J, and that determinant by K. We've got to find a way of being able to remember these, because even the 2 by 2 matrices here require some memory work. So here we are, let's go down and do it a different way. So if we put I, J, K across the top here, and A1, A2, A3, B1, B2, B3, that might be able to help us remember the system here. We don't have to go right up there. Remember the system here. Okay, now let's see what that system is. To get this determinant, this 2 by 2, and therefore its determinant, if we cover up the row, this is the I component, the row and the column that contain I, see that that's the matrix we want there? That's a little tricky-dicky use of matrices to get the right matrix, the 2 by 2 in there. Okay, now what do you do for the next one? Here's the next one we want to try and remember. If you cover up the column and the row in which J occurs, the 2 by 2 is this. Now this is a little tricky one, this one, because you don't actually want that determinant. See how they've switched it up here? In here it's A3A1, B3, B1. So that's got to go over there, and that's got to go over there, and vice versa. And then you will just plus it. Or, this is something I'm recommending, take it from here, and it's A1, A3, B1, B3. So you don't have to switch them, but put a minus there, because that gives you an equivalent answer. I think that's safer, so that you can still use your idea of crossing that out, and you don't have to change the order of these, but you need to put a minus in front, because that determinant is the other way around. So I don't know, what do you want to do? Do you want to switch them, or do that? Put a minus in front and keep them all the same. Now, let's look at the last one, the K component. Cross out the column and the row, and the matrix you want is in there. Okay, so matrices to the rescue here. This is the determinant of a 3 by 3, which is really used to determine whether a 3 by 3 matrix has an inverse or not. Now, we can use it because of this interesting pattern that we have to generate for these components up here. They are a big mess. Look at them. They are a big mess. So the components there that we're using, that arrangement is best summarized by the vector. So let's scrub that out and summarize what we've just done there. So here, if you want the cross product, put ijk across the top of a 3 by 3, then the two vectors a1, a2, a3, b1, b2, b3. Get the first one, you put that through, and it's the determinant of a2, a3, b2, b3 by I, and then go to the next line, do the j, and then it's minus a1, a3, b1, b3, j. Okay, so it's a nice little system, and then do the k, which is going back to plus because it stays in that order of the entries in the matrix, and that's k. Alright, so that's the idea here, and then of course you've still got to work out the number in front of I, a2, b2, this is the determinant, minus a3, b2. Right, you've still got to remember how to get the determinant of these 2 by 2s. Okay, it's AD take BC, AD take BC, and so you go on. Alright, that's a tricky way of remembering a hard arrangement of components. Alright, come down now and let's have a look. We've got a bit of a gap here for you again. Let's have a look at this one. And so here is a first example. Find A cross B. So there it is. They've done that and then gone on, but it's hard to remember that. So remember what it would look like here. Oh no, we've done it down here. So IJK with the vector A, vector B. They've got this. I'm suggesting to you, you come from here. Let's have a look. I, J and K. 2, 3, neg 1, neg 1, 2, 4. Cover that up. You're going to have 3, neg 1, 2, 4 by I. And then I'm suggesting you go this way and put a minus, and that would be then here the determinant of 2, neg 1, 4, no swapping around, by J. And then in the last column there, the last one is going to be 2, 3, neg 1, 2 by K, and then working out the determinants here. Okay, so that I'm suggesting you put a negative in front of that one to get that sign right. Alright, are you ready? Come and have a look at 4G1. First little 4 there. Okay, you're going to find some interesting things about A cross B and neg B cross A and things like that as you go through. Need to do all these problems, I think. All right, pause it. Let's have a look at the solutions in a minute. Here we go. Here are the solutions. Question 1, A to D. Just check you can do this. This is very important later. And question 2, hang on. We'll just go up a little bit there. Question 2. Coming down to question 3. Question 4. And let's go to another example and move on. Okay, here we are. We have 3 vectors in 3D land. B cross C, A dot B cross C, and the determinant of C. Okay, so I have a look at those. I think it's fairly straightforward. Again, I would probably say in here to use the negative and not swap that around. So your matrix here, I, J, K, would look like, what do we want? B cross C, 1, 2, 3, 2, 0, 4. And then in this middle component, it would be neg the determinant of 1, 3, 2, 4, J, rather than switch the entries around there. So study that. A dot B cross C, you then take this and you dot it with this. So it's that by that, plus that by that, plus that by that. Just bring in the dot product. This is called the scalar triple product, and I'll show you a way of doing that more quickly later on. The determinant of a 3 by 3 is, of course, what we said before. You're going to cover that and do that by the 2. And then here cover that and put minus 1, 3, 2, 4 by 1, because we're multiplying by these ones that we're crossing out, and the last one taking place of J would be 1, 2, 2, 0 by that neg 1. And that's a determinant of a 3 by 3. So check that, particularly if you haven't done matrices much at all. Matrices are arrays of numbers used for particular purposes, many purposes in maths. Interesting area. All right, let's come down and do some more. So here are some questions for you. 5, 6, 7, 8, 9 and 10. I think you should do most of these. There are interesting little results that are used and are necessary. Okay, so pause it and have a go, and I'll show you the answers. Here they are now. Okay, 5, 6 and 7. Just bring 7 up a bit. 7 there. 8, 9 and 10. Okay, come down and let's move along a little bit more. A plus B cross A, take B, simplify it, so there it is. And so it's A cross A, we looked at this in an earlier rule, take A cross B, okay, so there, just like FOIL in algebra land. B cross B, take B cross B cross A, take B cross B, and A crossed itself is going to be 0. Now, we saw that above, and also B cross B will be 0. Okay, we'll have a look at that again later, why that might be the case. So come down now, and let's have a look at simplifying these. Using vector product rules now, cross product rules, the idea of this here with cross and dot product. Okay, let's have a look at the proofs of those. Okay, so it's the idea of expanding that, like in FOIL, those results we proved earlier are valid here. Okay, let's have a look at a little bit more. Find all vectors which are perpendicular. All, look at that in italics, read the question carefully. Perpendicular to that. Well, what we would do, I still prefer this method. I, J, K, 1, 2, neg 1 for A, 1, 0, neg 3, and then going through, it's going to be 2, neg 1, 0, neg 3, I, minus 1 neg 1, 1 neg 3 J, and then plus 1, 2, 1, 0 K. And then doing those, you'll have neg 6, 2, neg 2, and you could take the neg 2 out the front. So the key direction vector is 3, neg 1, 3, and it could be any multiple of that, any scalar multiple here of that. All right, let's do some. So coming down to question 12 and 13, oh, we've given you the answers there, don't want to do that. So just come down more slowly here. There we are. Oh, you can still see the answers a bit. Find all vectors, watch the italics here. So it's a scalar multiple, they could be any length. and it could be in the opposite direction, couldn't it? K could be negative. Okay. All right, have a go. I'm going to show you the answers now. There's question 12. Let's now look at 13. There's 13. Okay, important questions these. It's getting a bit heavier now. Okay, let's have a look at direction of a normal to a plane. So there are 3 points on the plane. So let's make up vectors, A, B and AC. You could use BC because that's all in the same plane. All right, you could use BC here. Could use that. If n is going to be perpendicular to both of those two, here it is. It's the vector product, ijk by 2, 2, neg 2, neg 2, 3, neg 5, and so on. 2, neg 2, 3, neg 5 by I, take. Now by j, 2, neg 2, neg 2, neg 5, j, and plus 2, 2, neg 2, 3 by k. And then multiplying out these determinants here for the 3 components. Okay, and then taking out a common factor, taking out the direction that the vector's got there, and any non-zero multiple of that would do for a family of them. Okay, your turn. So here we are, question 14. Coming to the end, I hope you're not getting too tired. Have a go at that. This is very important. We're going to find the equations of planes later on, and also in that physics application it's important to see the notion of finding a vector perpendicular to two others. Okay, you must create your own vectors here. These are only points, notice. You must create vectors A, B, B, C or AC and so on. Let's have a look at the answers. There we have it. So check that. Alright, let's have a look. Here's our results. A cross B is a vector which is perpendicular to both A and B. A cross A is naught. Okay, we'll have another look at a proof for that in a minute. A cross B equals neg B cross A, opposite direction. So here, if you rearrange, it would be the opposite direction. But if you put neg B, it will be the same direction. There we are. A cross B and B cross A have same length, but in opposite directions. Okay, so here, the scalar triple product, now that's interesting, haven't used that. If you want to do A dot B cross C, instead of I, J and K up here, you could just put that, because then you're going to have B cross C coming out of that times A1, A2, A3 instead of I, J, K. So that's a useful thing that we're going to use in a minute. And then this idea of what we proved above, A cross B plus A cross C, and similarly for this one. Actually had a go at those above in the exercises. Alright, so come down and let's have a look at the last bit. And I think you saw with the physics application that we've got to have a direction. A cross B is a vector, so where does it go in 3D land? A cross B is equal to neg B cross A, and A cross B and B cross A are oppositely directed. You can do this with components. But what is the direction of each of them? If you do I cross J and J cross I, we saw in one of the exercises I cross J was equal to K and J cross I was equal to neg K. So let's look at it. I cross J went up there. So there's our cross product. And here J cross I went down there. So is there a way of determining this? If you've done some right-hand rules in physics, you'd know the answer to that. But come down and let's have a look. Here it is here. And here's a hand in the back here doing a right-hand rule in physics. We're not going to go through that. What we're going to do is do this up here. A cross B by the right-hand rule. If A is there and B is there, we've got to know that the direction perpendicular to that is up, not down. Okay, so B cross A is down, A cross B is up. And here's a little hand, and here's the rule over here. If you're doing X cross Y, use your right hand, where the fingers turn from, here we are, that's X, and that's y, and then this is the cross products direction up there. So try it on this one over here, where it's A cross B, and it should go up, and then you've got to turn your hand over to check this. So you might check with your teacher and your classmates. You can always laugh when there's a physics exam when they come to this question, because you can see everybody turning their hands around trying to work out the direction of the cross product. Okay, so this one down here I think is B cross QV, or length BQ sine V, which we'll do later on. So you need that right hand rule. All right, let's go down and do some. And here, before we do that, let's look at the length of A cross B. So there are the funny components that we've been using determinants to get. The length of it, therefore, is the square root of all that. But there's actually another geometric approach to this, and that is A cross B. The length of it is length of A, length of B, sine theta. Let's prove that. Okay, so that is useful, and it sort of validates also that A cross A, the length of that, would be length of A squared sine of naught at angle 0. So that would be naught, and therefore A cross A is 0. So there's another little check on A cross A's length being 0, or the 0 vector A cross A. Okay, so here we are. If we take this and we square it, then we get the length of 1, and this is by 1 take cos squared, and you'll see why in a minute, calling sine squared 1 take cos squared, from sine squared plus cos squared equals 1, from that one. Okay, so here we've got length of A squared equals this one, and here we can say this is A dot B squared, and if we work those out, here we have the length of A squared, length of B squared, and A dot B squared is this thing here. There's A dot B in there and squaring it, and they've left the steps out. We get this thing here, which is the length of AB all squared. Okay, so a fair bit of factorising here. You might try to do that. And this thing here, therefore, is that. All right, well, have a look at that, but I think it is an important result, this in here, in terms of the geometry of the situation, the lengths and so on. Come down and summarise that. So if U is a unit vector in the direction of A cross B, then you can think of A cross B having a size equal to that, times by the unit vector. Remember that idea of unit vectors? We are, if you like, capturing the direction by unit vector. And that's an important geometric definition. So you've got the length of the vector and its direction, which is the cross product vector. Okay, here we are. A cross B is naught, means A is parallel to B. That's a consequence, isn't it? Because if it comes to naught and the vectors A and B are not naught, then sine of theta must have been 0, which implies there's no angle between them, which implies parallel. Okay, so that's not hard to understand. Non-zero vectors here though. A and B must be non-zero, as we've got it up here. All right, come down, nearly at the end now, and I've got the last little set of questions for you, question 1 to 4 here. Okay, very important, the geometry here, so study that carefully. Let's go down to question 5. There we have it. I pause the presentation, have a go. I'm going to ask you to look at the solutions now. Question 1. Question 2. Question 3 and 4. And question 5. Okay, well that's the end of this presentation. My question for you now is, what 3D application can we have for the vector product? What about things like volumes of 3D solids, things like that? Could you find a use there for generating a volume formula? okay, for some maybe odd-shaped three-dimensional solids. Okay, maybe they have to have a uniform cross-section. There's a hint. So think about that for the next presentation, and I'll catch you then. Cheers for now.